So what we've been doing has been leading up to the concept of the antiderivative. We've been working on area, and we've been working on area done geometrically, area done with fnint, and then our final tool to find area is the concept of the antiderivative. And so if we define f of x as a function, then in notation, we use capital F of x to denote its antiderivative. In other words, we're going backwards, and the rules that we worked with before are just going to all be reversed. So, for example, we have the power rule for derivatives. The power rule says if you have x to the n, then in derivatives, you move the n down, and then you decrease the power by 1. If you're going to do that backwards, and you're going to work through the antiderivative, and you start with the power n, well then to do that backwards, you need to increase the power by 1 first, and then you need to divide it by that higher power as a quantity. And so that does the reverse to finding the antiderivative. So it undoes what you had just done. So for example, if we have x to the third, its derivative is 3x squared. But if we have x to the third and we want to do its antiderivative, then we're going to raise that power up to 4, and we're going to divide it by 4. And the way you check that is just by taking the derivative to make sure that you get back to x cubed if you do take the derivative, and it does work to work backwards like that. Now, antiderivatives always come with a constant added on to the end. We need to represent that constant because it could have a derivative of 0, which would lead us to a whole family of antiderivatives. Let me show you what I mean. So if you've got a function that's defined as g of x, and g of x is x squared minus 3x, and you want to find the antiderivative of that, so we denote that as capital G of x. Well, then the antiderivative of the polynomial piece will be x to the third divided by the power 3. It will be 3x with a new power of 2 divided by the number 2, and then there is a constant added on to the end. Now, why do we do that? Well, if we check our answers, there could be some constant value. It could be plus 7 or minus 14 or plus pi. There could be a constant there at the end of that polynomial, because when you take the derivative of that, it will become 0 and it will disappear. So we have to represent what that constant is every time we take an antiderivative. Other examples we work with need to be what we recognize. So for example, if we have f of x defined as cosine of x, we need to know that the cosine of x, capital, that its antiderivative is the function that came before it, which was sine of x. But there's also a constant added on to those trig functions as well. Another trig example might be h of x being defined as the negative cosecant squared of x. The antiderivative of that is the function we know that came before the negative cosecant squared of x, which is the cotangent of x, and then that would have a constant added onto it as well. Other constants that we recognize, perhaps we have r of x defined as 1 over x squared. Well, you're going to want to think of that as x to the negative 2. When you take the antiderivative of that, you're going to increase that power. And when you increase that power, it becomes negative 1. Okay, that power goes up, and you're dividing by negative 1. So overall, we're at negative 1 over x plus that constant c. Now, what if you have 1 over x? What if q of x is 1 over x? What is the antiderivative of that? Well, 1 over x is a special function that had what function came before it. And the only function that comes before that is the natural log of x. Now there's something special about the natural log function. Its definition as an antiderivative is the only one that requires absolute values. So when you take the antiderivative of that, you're going to have absolute value around it plus the constant c. So that would apply to anything that's a linear function, 1 over x minus 2. Well, its antiderivative, m of x, would be the natural log of x minus 2, but it also would need to be in absolute values with the constant of c. So this whole idea of an antiderivative is connected to the idea of area. And so that's where we need to make this final connection. This is called the fundamental theorem of calculus. This is part 1 of the fundamental theorem. Part 1. The fundamental theorem says that the area under any curve related to the x-axis can be found exactly with no error by computing the antiderivative of that function plus the constant c. And when we compute an antiderivative, the notation becomes a bracket now at the end. It's like we're finished, we've done the antiderivative, still from the values of a to b. So that's the computation of it. You find the antiderivative, then you evaluate that. And the antiderivative would be evaluated with the number b plugged in. So f of b plus c evaluates first. Then you plug in the letter a to f of b plus c, that gets plugged in second, and you subtract. This is what's called the fundamental theorem of calculus. So basically it's saying that you can use the concept of an antiderivative to evaluate area under any function. And so we will evaluate some of these. So for example, let's suppose that we want to do from -1 to 2, and we want to find the area that would be under the w-shaped function, the quartic function, 10x to the 4th minus 6x squared plus 3 along the x-axis. So first we need to find the antiderivative of that. So the antiderivative of 10x to the 4th is 10x to the 5th divided by the power of 5. The antiderivative of 6x squared is 6x to the 3rd divided by the power of 3. The antiderivative of the constant 3 is 3x, plus the overall constant c. That is going to be evaluated from -1 to 2. So you'll want to simplify that. That's 2x to the 5th minus 2x to the 3rd plus 3x plus c, evaluated from -1 to 2. And we start by plugging in the number 2. So this will be 2 times 2 to the 5th minus 2 times 2 to the 3rd plus 3 times 2 plus c minus, and then you plug in the number -1. So 2 times -1 to the 5th minus 2 times -1 to the 3rd plus 3 times -1 plus c again. And then we'll come up with a numerical value, and that numerical value will represent the value of the area that was underneath that curve. So we're looking at 64 minus 16 plus 6 plus c plus 2 minus 2 plus 3 minus c. We ended up with a value of 57, which represents the area under that quartic curve between that and the x-axis. Another equation that we might try and find the area of might be the integral of sine of 2x dx. So what that curve, and let's say between the bounds of pi fourths and pi halves. So what would be the area bounded under that? So we can use the fundamental theorem, which says, all right, find the antiderivative of that. So the antiderivative of sine is not cosine, that's the derivative of sine. The antiderivative of sine is negative cosine 2x. Now, just like with derivatives, we had to remember the chain rule. With antiderivatives, there's the anti-chain rule. The chain rule, is it regular, says to multiply by 2. The anti-chain rule says to divide by 2. And there's still plus c. So we've got our antiderivative evaluated from pi fourths to pi halves. And so when we evaluate that, we'll have negative cosine of 2 times pi halves, so that's just pi, over 2 plus c, minus negative cosine of 2 times pi fourths, which is pi halves, over 2 plus c. And we know that the cosine of pi is negative 1, so this will be negative 1 over 2 plus c. We know that the cosine of pi is 0, so this would be minus 0 over 2 minus c. So we're looking at an overall value of 1/2. I'll try and show you one of each. How about the antiderivative, the integral, of the function negative 1 over the absolute value of x times the square root of x squared minus 1, as its values go from 2 to 2 over rad 3, relationship to dx. Now that might look scary at first, but you think about, I've seen that before. What's the function that came before that? And hopefully you remember that that's an inverse trig. That is, oops, not negative, that is the cosecant inverse of x. That's the function that came before. That's its antiderivative, because the derivative of inverse cosine is that negative function, plus the constant c going on the values from 2 to 2 over rad 3. Which means we can now substitute, and we'll have the inverse cosecant of 2 over rad 3 plus c minus the inverse cosecant of 2 plus c. I prefer to evaluate those as sine inverses. So that's the sine inverse of the reciprocal, rad 3 over 2. That's just easier for me. The cosecant inverse would be the sine inverse of 1/2 plus c. So my sine inverse of rad 3 over 2 is pi thirds plus c, minus my sine inverse of 1/2 is pi sixths minus c. So I have pi thirds minus pi sixths, which is pi sixths. Another antiderivative we might want to evaluate is the antiderivative of an exponential. How about 5 to the 3x dx, going from 1 to 4? Okay, the antiderivative of 5 to the 3x. So sometimes when I forget how to do it, I think about what was its derivative. So its derivative, 5 to the 3x, its derivative was 5 to the 3x times the natural log of 5 times the chain rule of 3. So its antiderivative is going to be similar, except instead of multiplying by those chain rule things, we'll be dividing. And so the antiderivative is 5 to the 3x divided by the natural log of 5 and also the value of 3, plus the constant c evaluated from 1 to 4. So when we substitute, we'll be looking at 5 to the 12th over 3 ln 5 plus c minus 5 to the third over 3 ln 5 plus c. So we have 5 to the 12th over 3 ln 5 minus 5 to the third over 3 ln 5, which can be simplified. You can pull out what they have in common. We've got 5 to the third over 3 ln 5 as the common value, leaving me with 5 to the 9th minus 1. That would be another way that you could write that answer. Just a couple more, maybe evaluating the antiderivative from 4 to 7 of 1 over the function 2x minus 1. I showed you this antiderivative a little bit earlier. 1 over anything is going to be a natural log, or 1 over a linear term, I should say, a linear power 1 is going to be a natural log. So this is the natural log. Now 2x minus 1 needs to be in absolute values. And just as the chain rule would require me to multiply by 2, the anti-chain rule requires me to divide by 2, plus the constant going from 4 to 7. So I'm going to have the natural log of the absolute value of 13 over 2 plus c minus the natural log of the absolute value of 7 divided by 2 plus c. So we have 1/2 of the natural log of 13, which doesn't need absolute values because it's already positive, minus 1/2 times the natural log of 7. So I notice that they have 1/2 in common, and then the properties of natural logs tell me I can write that as a quotient, natural log of 13 over 7. Okay, our final one is not going to be an integral, but it's going to be find f of x, find the polynomial, given that f of 0 equals 4, and given that lowercase f of x is e to the half x. So we're asked to find capital F. We have lowercase f, so we need to perform an antiderivative. So the antiderivative e to the half x is e to the half x divided by, now remember last time the chain rule required me to multiply by the natural log of e and multiply by half. So this requires me to divide by the half and the natural log of e, plus the constant c. So when I clean that up, I'm going to have 2 e to the half x plus c. Now I know that f of 0 equals 4. That means if I plug 0 in for x, I should have 4 as my y value. So 4 equals 2 e to the half times 0 plus c. E to the half times 0 is e to the 0, which is 1. So 4 equals 2 plus c, so c must be 2. This time we've figured out what the value of the constant is. And so my antiderivative in its final form is 2e to the half x plus the constant of 2, which we were able to figure out. So I hope you have a lot of success working with antiderivatives and then using antiderivatives to evaluate exact answers for the integrals. All right, work with each other, help out each other, and then let me know by email or whatever if there's something that you as a group can't figure out together. All right, thanks.